Okay, now that we've had a chance to take a look at some forcing functions that are periodic in nature, and we've also learned a new trick to being able to solve for the particular solution, that is the complexification method. We're going to do one more practice run, this time with another seemingly simple differential equation. We have our homogeneous part on the left-hand side, and so that's going to be our first step, is to find our y sub h. And in order to do that, we need to convert our differential equation homogeneous part into a characteristic polynomial. And one of the things you notice right away is this does not perfectly factor, right? So this is going to be a little messy. So rather than try to factor it, we're just going to jump right into the quadratic formula and say, okay, so it's going to be negative b, so negative 4, plus or minus the square root of b squared, so 16, minus 4 times 1 times 20, so minus 80. And all over 2 times a, which is just 2. So you can probably tell pretty quickly that this is going to turn into a complex number. So sure enough, we have negative 4 plus or minus the square root of 16 minus 80 is going to be 64. So negative 64 on the inside there. And all over 2, which is going to simplify down to negative 2 plus or minus 64 is the square root of 8, so that's an 8i divided by 2 gives us plus or minus 4i. So we have two s values. They just happen to be complex. And so you might be looking at it and go, wait a minute, what do we do? Well, normally we would say something like our solution would be, just for one of these would be, we could say that y equals e to the negative 2 plus 4i times t, that right here. Since that's one of the s values, this is a particular solution. Particular solution for the homogeneous differential equation. That is definitely one. And the good news is this is totally expandable using our old pal, that's right, Euler. So we can say, that's equal to e to the negative 2t, going to factor that out, times, the other part is the 4it, and that's just going to be cosine of 4t plus I times sine of 4t. So this right here is actually our particular solution in an expanded form. But, and this is the good part, that means that there's a real part and an imaginary part. So we've got two parts that we can put together to get our general solution. And so the general solution is going to be a constant times e to the minus 2t times the cosine part plus another constant, and that's where the I kind of gets absorbed in. Another constant times e to the minus 2t times the sine of 4t. And so this is our homogeneous solution. So that's the first part, right? So it seemed like it was going to be scarier than it really turned out to be. But now we have to find our particular solution. And we're going to do that by complexifying our original equation, right? And so which part do we care about? Well, as we've mentioned before, since this thing has a cosine involved, we only care about the real part. Since the forcing function is cosine, we only care about the real part of our guess. And our guess for this one is going to be something like y sub c equals some alpha times e to the 5 IT. So if that's our guess, then we should be able to come up with our guesses: derivative, first derivative, and second derivative. So this is 5I alpha e to the 5IT. And our second derivative is going to be negative 25 alpha e to the 5IT. And so we're going to sub those in and see what happens, and see what kind of value we get for alpha. So if I sub those into my equation here, my differential equation at the top says take the second derivative, which we know, I'm going to keep up with the color coding here, negative 25 alpha e to the 5IT plus 4 times the first derivative, which is 5I alpha e to the 5IT, plus 20 times the original guess, alpha times e to the 5IT. And all that has to equal the right-hand side, but we're not going to leave it as cosine, we're going to complexify it. So this is still going to be the coefficient in front is negative 1, so we're still going to have a negative e to the 5IT. But again, we only care about the real. So I'm just going to remind us, only the real. And I write these notes to myself because as I go on, you can imagine you get like a half a page of work, and then you somehow forget which part are you paying attention to. So it's always good to kind of remind yourself, which part do I care about here? So if we continue the process, probably no big surprise, the e to the 5IT is in every single term, and so those all become ones. You can factor them out, cancel them out, however you want to call it, and we're left with negative 25 alpha plus 20I alpha plus 20 alpha equals just plain old negative 1. Right? So we have a total of negative 5 alpha plus 20I alpha equals negative 1. So you can think of it as alpha times negative 5 plus 20I equals negative 1. And we're solving for alpha, so a little bit of work. And we find out that alpha is equal to negative 1 over this complex number, which of course we're going to have to simplify by multiplying by its complex conjugate, negative 5 minus 20I, top and bottom. So that doesn't change anything. And when I do that, I'm left with, on the top, 5 plus 20I. And in the bottom, I'm going to have 25, positive 25. And then 20 times 20 is 400. And there's a negative, but then there's a negative from the I squared. So this becomes plus 400. So the end result is 5 over 425 plus 20 over 425 times I. And I'm fully aware that those simplify, right? So we'll simplify them when we get to the next step here. So that is the alpha value that makes our guess correct. It's a complex number, but it works. Now if we were to stop right here, take that, throw it in for alpha, and then stick that back into our original differential equation, we'd find out that on the left-hand side, if you plugged it all in correctly, it would be equal to, the real part of it at least, would be equal to negative 5 cosine of 5t. So now what do? Well, we say, I know my particular solution. After all, this is going to be this thing right here, this alpha. 5 over 425 is going to be the same thing as 1 over 85. And 20 over 425 is going to be 4 over 85. Right? And that's times I. And then it would be times e to the 5it. So there's my particular solution. Now, normally I'd be like, yay, I'm all done. Just add that to my homogeneous and we're all done. But I actually have to spill this out to find out what's the real part of this. And so I'm going to expand this by multiplying 1 over 85 plus 4 over 85i times the expanded version of this, which is going to be cosine 5t plus I times sine of 5t. And when I do that, I really am only concerned about the real part. So I'm going to multiply, to get my real part, I'm going to multiply this times this and this times this. Everything else is going to give me an imaginary number, or it's going to give me an imaginary component. And those are the only parts that I care about. So I'm going to write my real part. I'm just going to make a little note. Only the real part. And so I'm going to write my solution as 1 over 85 times cosine of 5t. And then 4 over 85i times I is going to be negative, so that's negative 4 over 85 times sine of 5t. And that, my friends, is my particular solution. Now again, that's the particular solution, but it's not the end of the problem, because the last step in all this, of course, is to combine the homogeneous with that particular. And so I can say my y of t is what I get when I combine the two, which is going to be k1 times e to the minus 2t times cosine of 4t plus k2 e to the minus 2t times sine of 4t. That's my homogeneous part of the solution. And then my particular part's coming from these two terms here, plus 1 over 85 cosine 5t minus 4 over 85 sine of 5t. And that is the solution. And of course, we can check that with Maple to make sure that we did it right. There's no initial conditions for this one, but it does the trick. So what made this one tricky was we had a imaginary values for our, basically for our eigenvalues, for our homogeneous part, right? But we can jump right to the solution using the Euler expansion of one of those particular solutions and get our homogeneous part. Put that together with the complexified process that found our particular solution, and we wind up with our overall general solution. So that gets us to the end of 4.2, and you can do some practicing with your problem set, and in class we'll do some practicing as well.